to welcome all the participants and give you the floor to start the second day sessions.
Okay, thank you, Engineer Omar. Thank you. So, good morning to everyone. Today, I want to start off with the examples that we didn't get a chance to see yesterday. So I have an assortment of some relatively simple examples, which we'll try to show you how all of this machinery of the GUM with regard to the uncertainty evaluation is actually handled and done. So my first example is, if you remember, we said that specifications and tolerances are not uncertainty. However, I mentioned at that time that they can be used in order to calculate an uncertainty. So my first example will show you how this is done. So I'm going to use the manufacturer specifications in order to calculate uncertainty for measuring devices or results that come from measuring devices. So I have here a couple of pressure gauges. Um, the first one is rated to an accuracy of 0.25% of full scale. Okay, so we have to make a distinction here. There are two ways of specifying the accuracy class of the gauge. One is with regard to the accuracy of full scale. The other is the accuracy of the reading. So someone has to be aware of this and take it into consideration whenever they are actually trying to acquire such a device and when looking at the specifications and when using the specifications in order to provide uncertainty estimates for the measurements that are performed with this device. So the first one, as I said, is a 0.25% full scale accuracy device. It has a full scale of 1,000 bar. Um, so uh, it's customary in pressure to use units other than SI units. The bar and the PSI is not quite SI. So if we were to be using the SI units, we would be talking about megapascal and kilopascal. So 1,000 bar device is 100 megapascal measuring device. And I based on this accuracy class specification, I will convert it into an uncertainty. So I don't know anything else about this device. So my assumption is that I have no reason to believe that errors generated by this device will be distributed in any other way than within the limits of the accuracy class. So this is what an accuracy class means. It means that it's not expected that you will see errors which are larger than 0.25% of whatever the full scale is, in this case, 1,000 bar. So that being the case, my assumption is a rectangular distribution, which has definite lower and upper limits, and no other assumption about how the actual measurements or the errors corresponding to those measurements are actually distributed within these bounds. Okay, so the first thing I want to do is I want to see to what pressure this accuracy class corresponds. So I have to multiply my percentage with the full scale to see what these limits are. And this is what actually is done in this first row here. So I'm translating the accuracy from a relative value, 0.25% of full scale, to an absolute value with units of pressure. So 0.25% is this fraction here. And because it's a full scale, I'm multiplying by the full scale, and I'm seeing that actually my errors are plus or minus 2.5 bar. Okay, so this is what the limits of my errors are. So once I have the limits of the errors, then I can, and the assumption of a rectangular distribution, I can go ahead to calculate or estimate the uncertainty. So how is the uncertainty estimated in this case? Well, it's the half width of the distribution divided by the square root of 3. So the width is from minus 2.5 to 2.5, okay? And this is what does here. So it's 5 bar is the width of the distribution, divided by 2 and divided by the square root of 3. So finally, the uncertainty, which corresponds to measurements performed with a device of this accuracy class, when the full scale is 1,000 bar, is 1.4 bar. Okay. Are there any questions? Okay, good. Well, the second example resembles the first example, but I'm also putting into the picture now the classification with regard to percentage error of reading. So this particular device, up to 20%, is accurate to within 0.02% of full scale. Okay. And from 20 to 110%, it's accurate to 0.1% of reading. Okay. And the full scale of this device is 30 psi. So performing again the performing again the same type of calculation. The first thing I want to do is I want to convert these relative accuracy or errors, which specify the accuracy, into absolute values. So I do this for the first part of the full range, which is from 0 to 20%. Okay. And I do it for the second part also of the range, which is from 20% to 110% with a different specification. That's why I have two accuracy values. So what have I done in the first case? Well, I'm using the 0.02%, which is this fraction here, and I'm multiplying it with whatever is 20% of the full scale, because up to 20% of the full scale is what I'm actually using this device with this type of a specification. And the second one would be then the 0.1% of the reading, and I'm assuming that in this particular example, the reading is 20 psi. So the numbers are not really that important. What is important is this distinction between the full scale accuracy and the accuracy expressed as a percentage of the reading. Okay. At any rate, in both instances, the uncertainty is calculated the same way. It's the full width divided by 2, so the half width of the distribution, divided by the square root of 3 because of the assumption of a rectangular distribution. So notice the word assumption. Okay, so it's up to me to assign the particular distribution which I think governs the spread, the dispersion of my errors. Okay, and the reason that I'm using a rectangular distribution in this case is because the accuracy class provides specific bounds within which I expect all my errors to lie. Okay, and because I have no idea of what the actual distribution of the errors within these bounds is. Okay.
Doctor?
Yes.
I have a question. Okay, we know that why we take rectangular distribution, which is A over square root of 3. This is the formula of rectangular distribution. And you divide it by 2 because K equal 2. This is manufacturer specifications. But why you have subtracted from 2.5, or you got the uncertainty of accuracy, you added a regular rectangular distribution, but you have subtracted as well. Why is that?
What do you mean I have subtracted? You're talking about the first example here, the first part of
Yes,
this example?
yes, the numerator.
So let me go through it again. The accuracy translated from a relative value into an absolute value is over here. So it's plus or minus 2.5 bar. Okay, so I expect all of my errors to fall within plus or minus 2.5 bar from the center, let's say, from whatever the average, the value that I'm measuring is. Okay, so the error cannot be larger than 2.5 bar either in the positive way or in a negative way from whatever I'm measuring. Okay, so then my full width of the distribution of the errors, the expected errors when I'm measuring with this thing, would be from minus 2.5 to plus 2.5. So it's this full thing here. The full width is this. Well, from minus 2.5 to plus 2.5, it's 5. That's what I'm doing here. So this subtraction here is done to show what the full width of the distribution is. Hence the 5. But it's not the full width of the distribution which is of interest to me when I'm calculating the uncertainty. It's the half width. So that's why I'm dividing by 2. So the full width divided by 2, that is the half width of the distribution. So this is A. A is 5 over 2. Okay? Divided by the square root of 3, which is the divisor based on the fact that I'm using a rectangular distribution. Does that clarify?
Yes, because you mentioned this is absolute uncertainty. If I want it as relative uncertainty, unitless, only as a percentage, is there an example for this one?
You would go through the same process, but you wouldn't translate it into an absolute number. So you would just start out with 0.25%. So it's plus or minus 0.25%. So the half width is 0.25%.
Yeah.
And that would be divided by the square root of 3.
Okay.
So it's 0.25% divided by the square root of 3.
Okay, I got it. Thank you.
Doctor.
Yes.
Doctor.
Yeah. Sorry. Yeah. I have just a question. The accuracy here, doctor. The accuracy class. I guess it is given by the manufacturer. It doesn't have anything to have with the resolution of the instrument. Huh?
Well, obviously it does have something to do, because the more, the higher the resolution of the instrument, the better quality of the instrument, so the accuracy class will be better. But there's not a one-to-one, let's say, correspondence between resolution and accuracy class. But yes, they are related. So the better the device, the better the resolution, usually.
Okay. So thank you.
Yeah.
Dr. Christos?
Yes.
I would like to apply this example if I am using, scales. And I know, from the standards that the scale is giving me an error or maximum permissible error within the range. For example, let's assume that from 0 gram to 25 gram is giving me based on the verification scales. Point E, it means, you know, the verification scales, I can, it's, you know, stated. So I can, you know the error from that. Can you consider it as a uncertainty and calculate it as uncertainty when I am using these scales?
Yeah, you can, of course. So in the beginning, I mentioned about tolerances, specifications, and I should add the idea coming from legal metrology, which are maximum permissible errors. So maximum permissible errors can also be used just like tolerances, and they can be used to estimate uncertainty values related to them. So if, for example, to make things simpler, if we're talking about weights, okay, then we know that OIML has a very definite hierarchy with regard to the accuracy of different weights. There are accuracy classes, E1, E2, F1, and so on and so forth. And there's a maximum permissible error associated with each one of these classes for each nominal value of weights. So that maximum permissible error can definitely be used in order to estimate an uncertainty value, a corresponding uncertainty value. Okay. What's the use of the maximum permissible error in that instance? It means that as here, as in the manufacturer's specification, that weights which belong to a specific class with a specific nominal value are expected to have errors, deviations from the nominal value within that range. So it's not expected that you will have anything outside of that maximum permissible error with regard to deviations from the nominal value. Okay. So yes, exactly the same. So the way that the calculation is done here using manufacturer specifications, the same way you can use maximum permissible errors. For balances, if the maximum permissible error is, let's say, within a specific range, one verification interval, you can use that verification interval to estimate an uncertainty value. Okay, so
Doctor,
yeah,
it means that I combined the uncertainty of the scales error or maximum permissible error to also the uncertainties that has been specified in the calibration certificate.
no, you don't combine. Well, there's, with regard to the calibration, and this is something that I come across in all of the labs that I see when I'm doing assessments, it's not really clear in everybody's mind that the uncertainty values that they estimate are valid only after they make corrections for the errors of the measuring instrument. So uncertainty values calculated are valid only after corrections are made. On the other hand, when someone, at least in mass metrology, when someone talks about maximum permissible errors, the uncertainty and the allowed maximum deviation are kind of blended together in this maximum permissible error. Did I answer the question or no? Did you ask something different?
The things, doctor, that when we are calibrating the weights, always we are using the uncertainties from the certificate to consider the uncertainty budget.
Yeah.
But today we learned that also the scale has the error from the scales also contribute to the uncertainty.
Yeah, the uncertainty from the calibration is a component of the uncertainty budget.
That's right, but again, I want to make, to stress this point that when you have a calibration certificate, there are two pieces of information on there, and we shouldn't be forgetting that basically you calibrate so that you can account for any systematic errors that your device might show. So one piece of information is the correction, the error or the corresponding correction that I have to make to the instrument's indications. And the other piece of information is, well, how sure am I about this correction? Well, that's the uncertainty. So uncertainty values on a calibration certificate of any sort are strictly valid only after the designated corrections to the indications of the instrument are made. And this is something that slips our mind in many cases because everybody's focused on uncertainty. But really, what a calibration certificate gives you, that's the basic element of a calibration certificate, are the corrections that you have to make. It's not the uncertainty, it's the corrections that you have to make. And then once you make the corrections, you have some residual effect, which is accounted for by this uncertainty value. I hope that everyone understands this because it's a very, very important point. I mean, the basic information on a certificate is not the uncertainty. It's the results of calibration are the corrections that you have to make.
Dr. Christos.
Yes.
But I think most of us, they are using the uncertainty, by dividing it, by square 3.
Wait a minute. I'm not talking about using. I'm talking about the contents of a calibration certificate. Okay. So when someone reads this, you should take away two things. One, the errors, and the second, the uncertainty.
Doctor, in ionizing radiation for SSDS, for the calibration of ionizing radiation detectors, when we receive the certificate, the calibration factor is stated as, for example, the calibration is 50.1 plus or minus 0.20. Either it is as an absolute uncertainty or as a relative, and it is stated below that the uncertainty is given for 95% confidence level between bracket k equal to. So for our certificates for the SSDLs, the uncertainty, the value that is given in the calibration certificate, it is either an absolute or relative uncertainty, overall uncertainty. It depends because some instruments, actually, I agree with you. Some instruments, they give just the difference. I mean, they make the comparison. They give you the difference between the measured value and the reference value. And this is actually not an uncertainty. This is some kind of error. I agree, totally agree with you. It depends on the certificate.
Yeah, but okay. So there are many variations to this. So the result can be given as an additive correction. It could be a calibration factor, which has a nominal value of 50, but after the calibration, it's 53.5 plus or minus something. So in order for the uncertainty to be valid, that plus or minus something, in order for that to be valid, you actually have to use the actual correction factor as determined through the calibration. So you have to use 53.5 and not the nominal value of 50. Okay, so if you use the nominal value of 50, then the uncertainty is not quite the value that's stated on the certificate. So I hope this is clear to everyone that, from a calibration certificate, you get this, the basic element is this correction that you have to make, either as a term or as a factor, a multiplicative factor. But the correction is the basic piece of information that's contained within the calibration certificate. Okay, are there any other comments or any questions with regard to this?
Dr. Christos, I was just going to say that for pressure gauges, people need to remember, though, the drift of the device, because over the course of a year, this device is going to be different than the correction factor from the certificate.
Yes, that's true. That's true, but that goes a little bit beyond what I'm saying here. What I'm
No, I got you.
definitely the information contained in a certificate is strictly valid, again, up to the time that the device leaves the calibration factory's door to be returned to its owner. So, you know, after that, it's up to the user to decide what he's going to do with it. If he's going to, you know, just use that value, or if he's going to assume that it changes in a certain way. So it's up to the user to actually decide what to do with this instrument depending on what the particular circumstances are. So I agree, yes, definitely. For any instrument, any um, uh, electronic instrument, or yeah, and mechanical instruments also, there's the situation of them drifting, and other times it's more important than in other circumstances. And someone would have to take account of that when they're using the instrument and they're trying to um, develop their own uncertainty budget for the use of the instrument. But that's, I'm just trying to show here how you can change a specification or a maximum permissible error, as it was stated, into an uncertainty estimate.
Yeah,
but
absolutely.
there are many things that can be said in addition to that, I'm sure.
Yeah, no problem. I just wanted to say for pressure gauges, I know that people usually use the uncertainty of the certificate, and that's it. And
Yeah.
it sometimes gets them.
Yeah. So if I wanted to make a point about what you're saying, I would say that it's not enough to use the uncertainty on the certificate, but you have to correct the indications of the device. And from what I am seeing from many labs that I go around, not everyone is aware of this fact. They think that, well, okay, I'll formulate an uncertainty budget. I'll take the uncertainty of the whatever's on the certificate, and I'll put it in my budget, and that's it. But that's half of the story, really. Okay. My next example is a little bit more involved, so I'm not quite sure of how aware you are of this, but I want to discuss about changing analog measurements into digital representations, and the problems that someone might come across because of this conversion from analog to digital, and because of the finite digital resolution that measuring instruments have. So our real world is analog. So what does that mean? That means that if I were measuring, let's say, a temperature or the barometric pressure, and I had a chart recorder in order to do this, so I was measuring to see what the signal is over time continuously, I would get some kind of a continuous curve, okay? Or if I am sampling my measurement of my real measurement, if I'm sampling it at specific time intervals, then I would see a variation which pretty much resembles this continuous variation. And if the time interval of my sampling becomes smaller and smaller, then I would expect this discrete measurement to coincide exactly with this continuous measurement. So my actual world, the things that I measure with my sensors are analog in nature, okay? They're continuous. Now, I have instruments which I use to measure what's going on around me, and then I interface these instruments with a computer, and I do things with whatever the measurements are. And computers work with digital in a digital fashion, not an analog fashion. So this initial signal, analog signal, is converted into a digital signal, and how well the converted digital signal represents the actual analog signal depends on how much of resolution I have available for my measuring device. So if I have, yeah, so I'll just leave it at that. The better, the more resolution I have, the more my sampled or my digital signal represents my analog signal. So I have a graph here showing on the right, showing this original analog signal as a continuous line. And then I have these dots here which show the conversion of this thing into a digital signal. So the first thing I can see is that from a continuous line, it becomes discrete points. The second thing I see is that these discrete points do not follow this line exactly. So they can follow it up to a point, but then they cannot follow the small variations that this continuous signal exhibits, okay? Why is this? Because of this finite resolution that the digital instrument has due to the electronics within it, the analog to digital converter. So this is called the fact that you have a finite resolution in converting an analog signal to a digital signal. This is called a quantization error. And the least significant bit of this conversion is the quantization level of the analog signal to a digital signal. So you see that all of these, let's see, 1, 2, 3, 4, 5, 6, 7, all of these discrete numbers, which as an analog signal vary, okay, here they're all represented by the same number. Why? Because these changes, these differences cannot be resolved by this A to D converter. Okay, so all measuring instruments then, all transducers which are used to measure some signal from the real world have this inherent error because of this finite resolution that they have, because of this least significant bit that is offered by their A to D converter. Okay, so in any type of measurement that we perform in the lab, whether it's a measurement of pressure, barometric pressure, or whatever, or any type of calibration that we do, comparison measurement, there's always this error present because the instruments have a finite digital resolution. Obviously, the same is true for analog instruments, by the way, but I'm not going to discuss that because I think it's evident there. You can estimate the resolution is fairly simple to get from either the graduation of the device or estimated somehow as a fraction of the graduation of the device, depending on how well my eye can resolve whatever I'm looking at. So I'm focusing basically now on digital instruments, okay, where we cannot see much. We can only see some digit changing, and hopefully that's the last digit that we see changing whenever we're making a measurement, which shows that, well, and I'll leave it at that. And that last digit that's changing corresponds to this least significant bit, the quantization error that is prevalent in any such circumstance. So how do we handle this? How do we change this error into an uncertainty? Okay. So what I have here, the graph on the left shows how the digital output of my measuring device, varies with an analog input. So I have a transducer which produces some kind of a signal, an analog signal. This is input into my measuring device. And on the screen of this measuring device, I get some number, which is a digital output. So what's characteristic is that there are, for a range of input values, I get only one output value. So in this case, anything between 0.5 and 1.5 will give me a value of 1. Anything between larger than 1.5 to 2.5 will give me a value of 2, and so on and so forth. So I get this stepwise type of a behavior of the digital output because of this limited resolution that I have due to the quantization error. Okay, so this quantization error, then, the maximum value is half on this side, half a digit on this side, and half a digit on that side. Okay, and this is what this graph shows, that the error can vary anywhere between negative 0.5 digits from the actual value to 0.5 digits of the actual value, plus 0.5 digits. Okay, so again, I have definite bounds within which I expect the errors of my measurement to fall. And because I have definite bounds, but no idea as to where exactly, how exactly these errors are distributed within this range here, from negative half a digit to positive half a digit, I assume a rectangular distribution. So for my instrument, for any digital instrument, this is the situation. This is how the quantization error can be changed over into an uncertainty. So how is that done in this specific case? Well, because I'm talking of maximum or minimum and maximum errors of negative 0.5 and plus 0.5 digits, then the full width is the difference between the two, so it's 1. The half width then would be 1/2, and I divide that by the square root of 3 because of this assumption of the rectangular distribution, and the uncertainty which is associated with this finite resolution, okay, of the instrument of 1 digit, okay, comes out to be about 0.3 digits. So this is an uncertainty which should be present in any type of calibration or measurement that we do, because we always use measuring devices in order to determine the result. And as I said, even for analog devices, the same is true. I mean, but it's much more evident what is going on there, because you have the graduation lines, which you can use in order to distinguish the readability of the instrument. Is there any question?
This one considered as a type A error?
No, this is a type B. Anything that's determined from the assumption of a distribution without the repetitive measurements is a type B evaluation. So type A is only from repetitive measurement. So whenever you calculate a standard deviation, then that's a type A uncertainty.
Okay.
Dr. Christos, you know, we have, when we are verifying the scales, we have a test called discrimination, I think, or
yeah.
Can we consider that the same when we are getting, you know?
Yeah, it's close. So, but I'm not getting into the details now of. So first of all, we have to distinguish between verification and calibration. Okay. So when you're verifying a balance, there are particular tests that you have to do to check the different parts of the balance. So one part that you're looking at when you're verifying a balance is to see whether the indication changes proportionally when the load on the balance changes, and that's the discrimination test that you do. Okay, so you want to see if it can discriminate the indication can discriminate between a small change in the load. Okay.
Yeah.
So it
this,
resembles this.
So we can. It's the same. It looks to me that it's the same. You are, doing the same as the, you are converting the analog to digitals.
Yeah.
Is that the same?
Yeah, I would say that if we're talking about a balance, then what I am actually saying here is that this balance has a readability. Okay, so when you
Yes.
buy a balance, an analytical balance, for example, it says 220 grams with a resolution of 0.1 milligrams. Okay, so that means that the least significant digit of this balance is the fifth digit when I'm talking about grams. Okay.
Mm-hmm.
Sorry, the fourth digit when I'm talking about when I'm using units of grams. Okay. So you use that readability of the 0.1 milligrams in order to determine the uncertainty which is associated with it. Okay. So that's my basic approach. So in calibration, you don't do a discrimination test, really. However, you do want to estimate what the uncertainty associated with the limited resolution of this balance is. So in order to do that, you use the information that's provided to you by the manufacturer, which is the readability or resolution of the balance. Is that understood? Is that clear?
Thank you. Yes.
Okay. Typically in calibration, this type of an uncertainty is included twice, because usually when you do a calibration, it's a comparative measurement. So you compare one state with another state. So you have to include this type of a resolution in your uncertainty budget twice in most instances. So you're comparing a loaded state with an empty state, for example, or something of that sort. So it has to be included twice. Okay, so this is, I don't know if there are any other questions regarding this finite resolution. I just wanted to make clear, because many of you use this and you say, well, what's the resolution of the balance? 1 milligram. Okay, I divide that by 2, and then I divide by a square root of 3, and that gives me the uncertainty. Well, why is that? Well, I just told you why this is so. My next example is a simple example of a combination of uncertainties. So I have a rectangular plot of land which has sides, let's say length of 210 plus or minus 20 meters and width of 125 plus or minus 10 meters. And for some strange reason, I want to find the perimeter of this plot. So I want to find the total length of its sides. And I want to estimate the uncertainty of this perimeter. So in order for me to do that, in order to find the perimeter, I have to add, obviously, all of the sides. So my measurement model here would be that the perimeter is A plus B plus C plus D. Okay. And that would give me a value once I substitute in the numbers corresponding to these, the lengths of these sides. And then I want to estimate the uncertainty. Well, it's a simple case of adding the squares of the uncertainties. So the combined standard uncertainty of this perimeter would be the square of the uncertainty of side A plus the square of the uncertainty of side B, of C and D. And I would, if I plug in my numbers, I would find something of the sort of 32 meters. So then this perimeter would be the length of the perimeter of the fence, or the plot, sorry, would be 670 meters plus or minus 32 meters. Okay, so it's expected that the perimeter, with a very good chance, in this case, since I'm talking about a standard uncertainty, that would be around 70%. Okay, the probability would be around 70%. that the actual perimeter is within 670 plus or minus 32 meters. Okay, so this is an example. Yeah.
I wish all the uncertainty calculated like as easy as this example.
Yeah, well, what it depends on where you're coming from, actually. I don't know what type of measurements you're involved in, but there are many measurements where this additive model is valid. Many measurements. So since I was talking about pressure earlier, and I'm sure that my colleague, Mr. Bryan, will agree that typically when you're doing a comparative calibration of a pressure measuring instrument, the model that you're using is an additive model. So you just have variables which represent with units of pressure, and you just use this this uncertainty budget. There are many instances of that sort. When you're calibrating a balance, for example, again, the model is additive. So there might be complications because of the terminology or things which are not really that much related to the uncertainty calculation itself, but the complexity of the actual situation in which you're in. But the uncertainty calculation, in many instances, is as simple as this. Instead of length, it could be pressure. Instead of pressure, it could be mass. So it could be kilograms instead of meters. I don't know, instead of meters, it could be Newton, it could be a force. So there are many instances, particularly when we're talking about calibration, comparative measurements in order to do a calibration, where your measurement model is an additive model. Now, I agree that if someone wants to go into a finer and finer scale of analyzing the situation, so the more detail that someone puts, the more difficult that your model might become, but that's another issue. The basic idea is what I just mentioned, that an additive model is very much prevalent when we're talking about comparative type of measurements. The second type of model that's very much prevalent is the multiplicative model. So I have the same plot of land, but in this case, I'm interested in determining the uncertainty of the area of this plot. Okay, so in order to find the area, my model would be the area is length times width. So that could be A times B, or because A and C are the same. So that's simple enough to calculate. And then I would need to find my uncertainty of this area. So because this is a multiplicative model, it's advantageous to work with relative values instead of absolute values. Okay, you could work with absolute values, but you would need to do more calculations. You would need to find the sensitivity coefficients, which would not be equal to 1, okay? And so you would have to go through many more calculations with no particular gain in anything. So it's advantageous in this case to work with relative uncertainties. Why? Because I can add the squares of relative uncertainties to find the combined relative uncertainty of the area. Okay, so I just go through, I use my numbers in my formula here, which tells me that the combined standard relative uncertainty of the area is the sum of the squares of the relative standard uncertainties of the length and of the width. So I just plug in my numbers. What is this? The uncertainty of the length is 20 meters. The length is measured as 210. The uncertainty of the width is 10 meters. it's measured to 125. So if I go through the calculations, I will see that this corresponds to about 10%, and this corresponds to about 8%, or this corresponds to about 8%, and this corresponds to about 10%. And if I add them, it turns out to be 13%. Of what? Of the value of the area. Okay. So then the relative combined standard uncertainty of the area is about 13% of that area. So if I wanted to convert it into an absolute value, then I would just have to multiply this by the actual area value to find how much that corresponds to. So then the actual uncertainty of the area, not the relative, but the absolute uncertainty of the area would be the area times this relative value. The relative value is 13 over 100. The area is 26,250, and it turns out that it's 3,412. Now, there is an issue here of how many digits are relevant in this answer. So is it absolutely correct to say that the uncertainty is 3,412, given that I can measure length to only 20 meters with an uncertainty of only 20 meters and width with 10 meters? But that's a different issue. The answer is no. I would have to round to something which is consistent with the uncertainty with which I can measure lengths in this example. But as a number, this is what comes out. So I don't know if are there any questions with regard to this?
No.
Okay, that's good. Okay, so let me move on to my final example of making up an
Doctor,
uncertainty.
reminder.
Yeah.
Reminder, we have 2 minutes to go to the break.
2 minutes. Well, I won't be able to cover the example in 2 minutes, so I propose that we stop here and I continue with this final example after we come back. Okay?
Okay, we're gonna have 10 minutes break. Very quick break, just to get your coffee and get back.
Okay, all right.
10 minutes.
Okay.
Doctor, sorry, I want just to remind that the previous example for multiplicative model applies also for a division. Yeah.
I'm sorry, what was that?
The previous example for multiplicative model, it applies also for a division or multiplication.
Yes, definitely. Yeah, division is a multiplication between a number and an inverse of a number. So yes.
Okay.
Dr. Christos, this is your dog?
I think even the dog is requesting for the time break.
That's right. I think example shows, clear things when you are giving examples.
Yes.
I figure out that sometimes we are, it's not clear to us, especially when he is discussing, the use of the calibration certificates and the using of the correction factors for that.
Actually,
Yeah.
Because the calibration factor is actually a multiplicative factor, so you have to apply the same rule as was explained by Dr. Christos here. It's just one component of the overall uncertainty. You need to add it as a uncertainty component. Where there are actually many other uncertainty, as he explained yesterday. We have to take into account the influencing parameters during your measurement. Okay, Dr. Christos said maybe.
I don't know. In the practical sessions the week after, shall we bring with us some instrument that when we are doing calibrations, calculating the uncertainties based on that? I don't know if it's good to do practical, calibrations.
One simple instrument is a caliper, for example. We can bring a caliper or whatever. Yeah.
Can we do it in the training room to do that, or what? I don't know.
We have to ask the doctor, the expert will come to Abu Dhabi.
Okay.
Yeah, I hope we do it practical by hand to know it very well.
Yes.
So it could be, if we arrange to have some weights and scales and do calibration for the weights. Or I don't know what you are using, Dr. Arib, in your laboratories.
Yes, what we can do, what you can do, because it will be a workshop, as its name is saying. I think we have to go with practice. What I can do, since we will have many people participating from SSDLs, including of course the final SSDL. So what we can do, we can just bring an example of a calibration performed in SSDL with the real data from the calibration, and then do a practice. There's no problem at all. So we do just it's the same everywhere for the calibration. You compare the reference value with the measured value, and then you derive calibration factor or a calibration coefficient, and then you have to just to guesstimate or to think about what are the influencing quantities like temperature, pressure, distance, reproducibility of the measurement, and then we have to gather all these uncertainties and come up with the uncertainty budget. It's of course it's not easy, because each one can come with its own uncertainty components. There are some which are simple, other one are very difficult. We'll see, inshallah.
I think we need to arrange it in a very good way so that all benefit from this practical training course.
We need to arrange with the expert and then come up with the practical sessions. Yeah.
Okay. Doctor, get your coffee.
I think he went already for a break.
Who?
Coffee break,
Yeah, we are in break right now.
Sorry, because I'm not seeing the numbering. I mean, you have to put the chronometer on the screen as usual. Yes. Do we have an idea about who will come for the workshop? Dr. Christos will.
Yes, he is arranging the practical examples, but I don't know if doing calibration inside the training room could be realized, and it could be more practical.
Yes. Coffee now. Coffee 10 minutes.
بنترتاح شوية يقوموا شو 4 hours it's too much.
والله
هذول ايش يسووا اللي بتاكلهم؟
بيطلعوا يتشنجوا اللامس من اصفر الى ابيض. هذول وهذا ايش يعني مو
Also this one.
All of them.
All of these. متى هذه الغرفة اللي اليوم؟ No, tomorrow Friday. Sunday. Friday, Saturday off. Yeah. لما كنت
I told them to change this too. They changed already this one many times ago. This are yellow.
Yeah.
It's really.
Yeah. Also, you see, you can see our very
Dr. Christos, can you hear me? Are you back?
Hello?
Yes.
Okay, for some reason, it was muted. I don't know what happened here.
Actually, it's my fault. I mute all because
Oh, I see.
I start to hear, some conversations from one of
Okay.
our colleagues. So we don't want to, to hear these conversations.
Okay. All right. So, are we ready to continue, I guess?
Yes, it's time.
Okay. All right. Good. Let me try resharing again. I hope it'll work as well as it did the first time around. Can everyone see my screen?
Excellent.
Okay. All right. So my final example, simple example. I should say that
Sorry, Doctor, I cannot see your screen.
I don't know. Is there anyone else?
Maybe you have a problem with Aisha with us.
Yes.
Yeah, you have. We are seeing it. It's normal.
Okay, I will go and come back.
Okay.
All right. So I wanted to say that obviously I'm presenting simple cases here. So in some instances, you might have measurement models which are more complicated than the ones that I'm showing. But this is an introductory course, so I don't want to, I'm assuming that there are people with different backgrounds and different levels which are actually participating. So I don't want to make it too difficult. However, for the second phase of this training, if someone wants to send me a measurement model that they are interested in to look at, we could do that. So I of course have some examples in my mind, but if someone has something which is particularly difficult and they're struggling with something, I would be happy to help if I can. So the final example of this uncertainty budget is actually taken from this very nice introductory uncertainty guide from MPL. So I'm trying to measure a simple measurement, the length of a piece of string, and using a tape measure. Okay, so the measurand in this case is the length of the string measured using a tape measure of a particular resolution. If I needed to, I could make it more definite and say at a particular temperature and when the string is laid down on a particular flat surface and so on and so forth. So all of this not specifying, sorry, I hear a noise in my, and it's confusing me. I cannot concentrate. I don't know where it's coming from. Okay, thank you. So okay, as as I was saying, that all of the fact that I'm not defining the measurement to an extreme level, this could contribute to the uncertainty with which I determine the length of this piece of string. So the particular measurement was repeated 10 times, okay? And every time that the measurement was done, the tape measure was aligned with the piece of string from the beginning. So not as so that each measurement, each repetition would be independent. The average of these 10 measurements turned out to be 5.017 meters, and there was an estimated standard deviation of 0.0021 meters. So then the first thing that we can actually determine here from this example is the uncertainty of this mean, because I know that in order to find that, and this is a type A uncertainty evaluation, in order for me to find that, I would have to divide the estimated standard deviation with the square root of the number of measurements. Okay, so that would give me the uncertainty of the mean, indication from my repeated measurements. Okay, so this is a rather dense slide, but let's try to focus on it row by row. So my measurement model then, as it's shown in the first row, is that the true length of the string is equal to the tape measure indication plus any correction that results from the tape measure calibration plus any correction that results from the limited readability of the tape measure plus any correction that might be due to the way that the item behaves during this calibration. And I will make this clear as we go on. Okay, so this is my model. It's a simple additive model again, which relates the true length to the indication plus a number of corrections. So in this below in the green box, you see how this can be written a little bit differently to resemble more the usual way that measurement models are actually written down. Because
Dr. Chris?
if yes?
Sorry to interrupt you. There is a small message box appear on the equation under number 2. Can you hide it? Just click on hide.
Here.
Okay, thank you.
All right. So in the green box, you see this measurement model expressed a little bit differently, where I have moved, I've created the difference of indication minus true value, okay? And that gives me minus the correction due to the calibration, minus the correction due to the resolution, minus the correction due to the way that the item behaves. And because these are minus corrections, they're equivalent to errors. So you see here, this is a definition of the errors. The sum of the errors that show up during this calibration comes from the difference between the indication of the instrument and the true value. This is a definition of the error. Okay, so everything is consistent. This is typically how I minus y equals to delta cal plus delta res plus delta item would be the way that I would typically write down the measurement model. But if I change it a little bit around, then I write it like this, because in this situation which is a measurement, not a calibration per se. It's a measurement. I'm trying to measure a piece of string. It makes more sense to write it this way than it does to write it that way. Okay, so I hope that everyone understands what the distinction that I made here, and how I formulate my model. Simple additive. To the indication, I add a number of corrections. Now, some of these corrections turn out to be 0. Some of them are not. Even if the correction turns out to be 0, it doesn't mean that its uncertainty is also 0. So even if a correction is 0, has a 0 value, there's still some uncertainty associated with that, because 0 is just another number, just like any other number. Okay, so let's not confuse the fact that the correction is 0 with the uncertainty associated with that correction. Okay, so my input estimates to my model then are represented by variables I, C sub cal, C sub res, C sub item. And my output variable is Y, capital Y, okay? And through my measurements, I have estimates of the input variables, okay? So I'm grouping them into two categories, let's say. The variables that are, or the estimates that are associated with a tape measure, and the estimates that are associated with the item being measured, okay? Okay, so with regard to the first variable, I'm hearing a noise. I'm sorry, but it's very distracting. Is someone has their microphone open, please?
Yes, thank you, Dr. Chris. Amr, Sadiq, if you hear your, yes, thank you. Go on, Dr. Chris.
Okay, thanks, because I'm getting a headache with that thing. Okay, so the first variable is the indication of the instrument. So you see down here, this is the value that I got from, it's the mean value from my 10 repeated measurements. And the uncertainty associated with that is just the standard deviation from the 10 measurements divided by the square root of the number of measurements, 10. So this is the type A that I talked about, I mentioned earlier. From the calibration certificate, in this particular example, okay, this is not always the case, but in this particular example, I'm assuming that there's no correction to be made based on the results of the calibration certificate. However, there's an associated uncertainty with this 0 correction of 0.1% of reading. Okay, so the calibration certificate is issued at 95% level of confidence, and the uncertainty is 0.1% of reading. So then that would make the standard uncertainty associated with the calibration of the tape measure in units of length to be given by 0.1 divided by 100. I have to divide this by 2 because this is an expanded uncertainty at 95% confidence. So I'm dividing it by 2 to convert it into a standard uncertainty. And from a relative value, I want to change it over into an absolute value. So I'm multiplying by the reading, which is the mean value. Okay. The resolution of the tape measure, again, there's typically no correction that can be made. The correction is 0. However, there is an uncertainty which is associated with this correction, and typically this uncertainty is 1 division, so of the tape measure graduation. So I'm dividing this division by 2, okay, because I'm looking at, I'm interested in obtaining the half width, and then in order to change this into an uncertainty, I would have to divide it by whatever assumption I make about the distribution associated, and that's a rectangular. So I would have to divide that by the square root of 3, which I missed here. Okay, so the uncertainty is the division divided by 2 divided by the square root of 3. And the division the least division graduation on this tape measure is 1 millimeter. So measurements are typically accurate to 1 millimeter. With regard to the item being measured, there's a correction that is determined to be equal to 10 millimeters. So where is this coming from? In this particular example, it's coming from the fact that I was not able to always make the string without any kinks when I am measuring it with a tape measure. So I estimated that because of the kinks in the string when I'm laying it down in order to measure it, that there was an error on its length on the order of 1 centimeter, okay? Because it wasn't perfectly straight when I was doing the measurement. So because there was an error on the order of 10 millimeters or 1 centimeter, I have to make a correction to the indications, okay, obtained by my tape measure of 10 millimeters, so that I won't be underestimating the value of the length of the string due to the way that I'm performing my measurement. Obviously, if I was able to do this more carefully, then probably this correction would also be 0. Okay, so it depends on how careful and how elaborate I am in performing my measurement. So obviously, the more effort I put into something, the more gain I have. That means the smaller the corrections and the smaller the uncertainty associated. Anyway, I estimate that the uncertainty associated with this correction that I have to make is 0.2% of the reading. So then this would be 0.2 multiplied by 5.017, again divided by the square root of 3, since I'm talking about an uncertainty, because of the assumption of a rectangular distribution. Okay, so in order for me not to confuse you here, what I meant to say is that the uncertainty is gotten from this 0.2% of the reading. Okay, I didn't mean to have this represent the actual value of the uncertainty, because in the next slide we will see how these things are calculated. So again, my input estimates, they have 2 numbers associated with them, a value and an uncertainty of that value. Okay, and I calculate the uncertainties based on the information that I have with regard to my input variables or input quantities. Okay. The only case where it's not based on information, but it's based on actual measurements, is from the repeated measurements of the for the indication which is gotten from repeated measurements. Is there any question with regard to this?
Dr. Chris?
Yes.
I have just questions about the resolution. I think type A as the standard error of the estimator already includes the resolution error. For example, if we take 10 measurements and we just change the resolution, type A will also change. So isn't the resolution error already considered in type A?
Yeah, that's kind of a philosophical question. I'll put it a little bit differently. Let's say that we do 10 repeated measurements, and because of the resolution of the device, I get, so it's a crude device, crude resolution, I get the same number. So what's the type A uncertainty? 0, right? So I've seen situations of that sort where I have devices which are not very accurate, or I should say are not very responsive because of the limited resolution that they have, and you get a repeatability of 0. So that's not correct either. So there's no, I mean, that zero repeatability is not due to the measurement itself, but it's just due to the device. So you have to account for this somehow. And this is one way of getting around this. So I'm not answering the question directly. I'm kind of hinting at the answer. So yes, it could be that the resolution is included in the type A. So when you're doing repeated measurements, but what we're trying to determine doing the type A measurement are random errors, that is errors that are changing. Whereas the error that's coming from the resolution is a constant error. So that being the case, it's, I guess, a good idea because this is a systematic type of an error due to this limited resolution. So it's a good idea to include this extra term. So I'm kind of answering your question, but the nature of these two errors is a little bit different. So the error due to limited resolution is kind of systematic, doesn't change, whereas the error due to repeatability is random.
Yeah, thank you. And if you don't mind, I have another questions about the last item, the error.
Yeah.
Why did you assume that you have a rectangular distribution?
For which one? For the item being measured correction?
Yes.
Well, because I do not have any other information regarding this particular the error associated with this particular variable. So the only thing I know is that it's estimated to be between plus or minus 0.2%. So, and I have no idea of how this is distributed within these limits. So again, when this is the situation, then I have to assume the most general type of a distribution, which is a rectangular distribution.
Not to assume that it is a normal distribution, the default case of the error or the expected resolution of the error?
And I would not assume that it's a normal distribution here because normal distributions do not have definite bounds. You can find errors. There's a small chance that you can find errors all the way out. There's no limit to how large the errors can be. But in this case, because of the way that I'm approaching the problem, so you see, it's not 100% objective, okay? It's subjective in many instances. So I'm approaching this from this point of view that, well, I know for some reason, or I estimate based on my knowledge, that the maximum and minimum errors will be plus and minus 0.2% of the reading. And once I do that, then I'm kind of obliged to assume a rectangular distribution. If I had more information, I would be able to assume something different, but anyway, something that has definite limits. And the normal distribution does not have limits. It goes all the way to infinity. The errors do, I mean.
Yeah, I think with this assumption that I have a minimum and maximum range, yes, we can assume that it's rectangular. But if I don't have this assumption, I think the default or the normal assumption for the error is plus or minus 10, normally distributed around the mean value. But it's clear, okay.
I don't agree with plus or minus. Why would you say that?
Because it's an error around the mean value. So it's 10 millimeter. I think if we repeated the measurement, this 10 millimeter error or 0.2% will not be exact. It will be randomly fluctuated around the original value of the error.
Yeah. Okay. I mean, someone can look at it from a different perspective. However, I have to caution that it's risky. The least amount of risk in the estimate comes from assuming a rectangular distribution. Yes, it's a larger uncertainty, but it's always better to overestimate than underestimate. So I wouldn't put, I mean, unless there's good reason for me to believe that something else is happening, I would kind of keep away from um, doing something different than a rectangular distribution. So the assumption that you're making here is that, well, because this correction or error is minus 10 millimeters in this case, then errors will be distributed normally around this. But there's no reason why to assume that they will be distributed normally.
So rectangular is better. It's better because it has a larger assumption.
Yeah, based on the fact that it's the rule of thumb is it's better to overestimate than underestimate. That's the case. But I'm trying to see if there's any reason why. I mean, I'll think about it, and but unless I am. I have good reason to believe, as I said, that something else is happening or is valid, then it's always a good idea to stick with the rectangular distribution.
Okay, thank you.
Any other question? Okay, so then I want to show how this fits into the uncertainty budget. So this is what an uncertainty budget might look like for this particular problem. So you see, I have my table here where the first column is really just the names or the symbols for the different input quantities. The second column is the estimate. So let's see what the estimates are. So for the indication, it's the mean value that was calculated from the repeated measurements. From the calibration certificate, the estimate of the correction is 0. For the resolution, the estimate of the correction is 0. And for the behavior of the item being measured, I have a correction of 1 centimeter or 10 millimeters or whatever you want to call it. So then if I use my model to determine the result of the measurement, that is my closest approximation of the true value, then I would have to add all of these numbers and I get this result here. So the actual length of the string based on the values of the input quantities of my model is this value here. The next column is the error that's associated with each one of these estimates. So we talked about this. This is the standard deviation, the estimated standard deviation. This is half of the calibration uncertainty. This is the interval associated with the limited resolution, and this is 0.2% of the reading. In fact, sorry, I'll take it again. The first number, the 2.1, is the type A. It's the standard deviation. The other numbers are, for calibration, it's half of the expanded uncertainty, okay? For resolution, it's half of the division, and for the item, it's half of the full width, which is 0.2% of reading. And then I have to assume some kind of a distribution. We discussed this, so I'm assuming a Gaussian distribution associated with my indication, a Gaussian distribution associated with the calibration of the item, and uniform or rectangular distributions associated with the limited resolution and with the use of the contribution of the item itself. The divisor is the next column. And then I calculate the standard uncertainty. So this number here is the error divided by this number here, and so on and so forth. The sensitivity coefficients are 1 in this case, because it's an additive model, and all of these things have the same units. And the uncertainty component then is just the product of the sensitivity coefficient and the standard uncertainty, and they are listed over here. Okay, notice that my uncertainties are rounded to 1 decimal digit, and they're rounded to 1 decimal digit because of the measurements of the device that is available in order to perform this measurement. Okay, the device is has a resolution of 1 millimeter. Okay, because this number results from an average, I'm allowed to have 1 digit more. And this is the reason why I have 1 decimal place included in my uncertainty estimate. Then I determine the uncertainty by squaring and adding. Then I determine what are called the effective degrees of freedom, which I didn't talk about. But these are used in order to determine the coverage factor. And in this case, because the number of degrees of freedom is very large, the coverage factor turns out to be that of a Gaussian for a probability of 95.4%. And then I multiply these two and round to 2 figures, or actually I've changed the units from here from millimeters to meters. So actually, if this was in millimeters, it would still be rounded to the first decimal. Okay, so I'm not going into to describe the differences between significant figures and the decimal, but what I will say is that it's always a good idea to not quote uncertainty to more than 2 significant figures. Okay. And the number of decimals that you have in the uncertainty should be consistent with the number of decimals that you have in the measurement result. Okay, so you see the uncertainty has 1 decimal when it's measured in units of millimeters. The result has 1 decimal when it's measured in units of millimeters. So this is in meters. So I would have to multiply by 100 to convert this. I would have to multiply by 1,000 to convert this into millimeters. So it would be 5,027. And my result is 6.4. So I have 1 more digit here than what my result. And I'm allowed to do this because this is coming from an average value. So I could stop at 6 and say 6 millimeters, but it's not wrong to say 6.4. It would be wrong to say 6.4135, for example. Okay. Is there any question with regard to this?
Yeah, doctor, what we is amazing to see here is that even if you measure 0 for the two parameters, the uncertainty is still there.
Yeah.
Yeah.
I hope that everyone appreciates this. So the actual estimate is not the uncertainty, okay? So the estimate of the input variable to your model is not the uncertainty, okay? So that's the measurement. And because this 0 was determined through some kind of a measurement, there's an uncertainty which is associated with it, which is different than 0.
Exactly.
Okay, so this is, I think, my final slide here. So just to summarize of what I've been talking about over the past day and a half. So measurement, error, random and systematic, and uncertainty have different meanings. Okay, so error is not uncertainty. The latter can be described by statistical concepts relevant to measurements. So uncertainty is a statistical concept, and it's a probabilistic concept, and statistical methods can be used in order to estimate it. The guide to the expression of uncertainty in measurement describes in detail the methods that are used to estimate the uncertainty. I would add that in all of the other documents that are used as explanatory documents to the guide to the expression of uncertainty. Okay, and there are many of those. The standard uncertainty can be estimated either by statistical techniques or use of prior information. Okay, so if it's statistical techniques that are used, then we're talking about a type A uncertainty. If we're using prior information of any sort and the assumption of an underlying probability distribution, then we're talking about a type B calculation of uncertainty. Standard uncertainties are combined in a sum squared fashion after accounting for the fact that they may have different units. Okay, and this is basically a fancy way of saying this is to say that uncertainty is propagated. So we talk about propagation of uncertainty. The expanded uncertainty increases the level of confidence to 95% usually, associated with the interval which contains the true value. Uncertainty estimates and calibration certificates are stated with an expanded at a probability of 95%. So they are expanded uncertainty estimates. And the uncertainty budget is a systematic way of presenting the estimation of measurement uncertainty. So with this, I finished this this part of my of the presentation. I don't know if there are any questions that.
Yeah, doctor, I have a question.
Yes.
When it comes to calculating some parameters using a regression equation or polynomial fit or linear fit, so we apply the same model. I mean, model equation here to calculate the calculated value, and for example, for the linear fit, to calculate the uncertainty on the slope and the uncertainty on the y-intercept. So we have to follow the same model equation.
It's a little bit more involved, so it depends on what you want. It's a type A evaluation because it's coming from actual measurements, so they might not be repeated, but they are a number of measurements which are used to model the variation somehow. Okay, so it's a type A. Now there are several things that someone can say. am I interested in the uncertainty of the coefficients of my model?
Yes.
That can be done. It can be handled. Am I interested in the uncertainty of using my model in order to predict values? That can also be done, and that there is a way of estimating this uncertainty. I will get into this during the second part of this uncertainty training. So I will
nice.
talk about this the next
Excellent.
time around.
Excellent. Okay. Excellent. Good.
Are there any other questions? For some reason.
Thank you, Dr. Chris.
Dr. Chris,
Yes.
I have questions about concerning using the relative uncertainty component instead of estimating the sensitivity coefficient as you give in the example. Is this model is valid for nonlinear models?
So the use of relative uncertainties, if it's valid for nonlinear models, but yes, because the multiplicative models that I'm talking about are not strictly linear, so they could have different functional relationships. So yes, it's true. But what's the question? Is the question if we can use relative uncertainties, or if it's simple to add relative uncertainties even if we have nonlinear models?
Yes, this one. For example, in your example, the area of the rectangular was simply the multiplication of the length and the width.
Yeah.
If we assume that we have a model that y equals L multiplied W square, not W square. In this case, it will be valid to estimate the combined standard uncertainty using a relative, not to calculate the sensitivity coefficients for each component.
Yeah, but this simple model is not linear because you have the multiplication of two variables. So you have y equals L times W. So that's not a linear model. So multiplicative models in general are not linear.
Yes.
So I think that answers the question. So a linear model is more like an additive model than it is a multiplicative model.
Yes.
I mean, in this case, the sensitivity coefficients for each component will be simply the other component. The sensitivity coefficient of L will be W, and the sensitivity coefficients of W will be L. In this case, yes, the relative uncertainty expressions will be exactly as using the sensitivity coefficient. But if the area was, or the equations was LW square, in this case, using the relative uncertainty will be different than the expressions using the sensitivity coefficients. Am I right?
Okay. All right. Now I understand what you're saying. So if a variable appears as a power, is what you're saying in the model,
Yes.
then it will be different. Yes, it will be different. And the difference will be that power will be multiplying that relative uncertainty. And I think it's clear why this is happening, because when something appears as a power, let's say square, as you said, the uncertainty affects the final result twice. And that's why it has to be included twice in your uncertainty budget. So to say it another way, if you're calculating, let's say, the uncertainty in the area of a circle, okay,
Yeah.
then the uncertainty of the radius of the circle would be appearing in there twice because the radius is squared. So the measurement of the radius is extra important, let's say, because it's to the second power. Do you understand what I'm trying to say? So you're right. Yes, if something is raised to a power, then that affects the estimation. Yes.
Okay. Thank you.
Yeah, doctor. I totally agree with you because we have the same example in the calibration or in SSDS. We have the when it comes to the uncertainty of the distance, we know that the dose varies with your inverse square law, inverse square of the distance. So the uncertainty of the distance will appear twice actually.
Yes.
I have just a question. So we are basing our uncertainty calculations using the either the Gaussian approximation or rectangular, triangular. But what happens when the measurement actually doesn't follow the Gaussian iterative? For example, in case of Poisson's distribution, this is particularly seen in the counting when it comes to counting radio adjectivity. Uncertainty is one of the over square root of n. So do we have to follow the same rule? Same GOM rule, or even for this distribution?
Well, I'm not an expert in that, so I can tell you that I think that you would follow the same reasoning, okay? But you have to adjust for the fact that now you're talking about counts and you have a Poisson distribution instead of something else. But I would have to. I cannot tell you really.
I think the because of distribution, the Gaussian distribution is an approximation of a Poisson. So we need just to apply the Gaussian approximation, and that's it. Yeah.
Yeah, but we have to remember now. We have to make a distinction here of what we're talking about. Strictly speaking, remember we said that counting is not measuring. So
yes,
I am pretty much talking about measurements, not counting that much.
Yes. Thank you, Dr. Lee.
Okay. Any other questions? All right, then. I think that I should continue on with the second part of my presentations. However, I'm kind of confused now because I don't see anyone, and I see like I'm outside of the meeting for some reason. Can you see me? Because I have my camera turned on.
No, we cannot see you.
You cannot see me. Bear with me for a couple of minutes, please, okay? I'm not sure what's happening. I'm not sure of what's happening. I can see one colleague here.
Yeah, I think we have. Yeah, let's put the
Okay.
camera on all of us just to check. Omar, can you sort out this issue.
Yes, now.
So
Yes, now
can you
now
hear
we can see
me?
you. Yeah, now we can see you and hear.
You can hear me. Okay. Because I have a feedback here, and what I will do is I will switch off and come back on. Okay. Please bear with me for a few minutes. Sorry for this. Okay. Can you hear me now?
Yes.
Yeah.
All right. I have a feedback coming, and it's making my life very, very difficult. I don't know what to do about it. Okay, I would need to be given control again, so I can share my screen. Abdullah, can you hear me?
Yes, doctor. Do you have any problem?
Yeah, I have a problem. I have a feedback, and it's making things very difficult for me. I don't know how it's happening. I don't know what exactly is going on.
Feedback from
myself. I can hear myself.
An echo, you mean?
Echo, yeah.
But
If we have
the others, they have a problem.
we have to switch off
Doctor,
our
try to
mic.
remove
Maybe it's coming from the participants.
It could be my fault. I don't know.
We hear it. We hear the echo also.
You hear the echo?
No, I think Dr. Chris, you're joined twice.
Yeah, maybe.
You have joined.
Maybe that's the case.
So you have to mute one of your.
You can
channels,
mute you can mute one of your either your mobile. You are using your mobile.
No, it's not the mobile. That's why it's strange. I don't see two connections. I only see one connection. But that's right. You're right. It might be that there are two.
Engineer Abdul, I can see and participants. If you scroll down, others, MITSAS. This is your other email, Dr. Christus?
Yeah.
Yes.
Okay. This is not as a presenter. If you can, Abdul, you remove this one.
Okay, I will.
Or mute him. Just mute him. Maybe he.
Yeah.
So can you hear me now?
Yes.
But the echo is still there.
No. It shows you are muted, but I can hear you.
Yeah. So that's kind of strange, isn't it?
Yes, it means one of them muted, which is we keep it as it is. So is it now break time?
Maybe we can make it break time now, so we can fix this issue, because I don't know how to continue really.
You can sign out from one account.
Well, what I will do is I will close my connection and come back again.
Dr. Christos, now the solution has been solved. We cannot hear any echo. Do you hear echo from your side?
Yeah, I can.
Oh, okay.
Just disconnect and reconnect again. It may solve the problem.
Yeah. That's what I will do. But should we take a break for 10 minutes?
Yeah, yes, I think so. Omar.
So let's take our break, and when we come back, we'll continue till the end of today's session.
Doctor, can you go and reconnect? So we will stay with you because it's not the it's the time for another break. Okay, 10 minutes break.
All right. Okay. So I would need you, Omar, to stay there so you can tell me whether I can hear you, you can hear me, and what have you. Okay.
Doctor, all of us with you.
We are with
Okay.
Because nobody will go out.
So I will disconnect and reconnect again.
Dr. Christos.
Yeah, I disconnected.
So now can you hear me?
Yes.
We can hear you, but
I don't know what's going on because everything is closed. Teams is not open on my computer, and it seems like I'm connected. So I don't know what's going on really.
Yeah, you have some connection somewhere.
Make.
Okay, which one, Dr. Christos? Doctor?
Restart your computer.
Yes.
Are you by chance using Windows on
maybe
MacBook?
From the web, maybe from Safari, the web you are open.
Yeah, if it's MacBook, then you have.
No, it's not MacBook. It's not MacBook.
Okay.
Open your Safari or Chrome. Maybe it's there somewhere. Window open.
No, Safari is only for Mac.
Okay. So I think it's solved. You can hear me, right?
Yes.
Yes.
And you should be able to see me now.
Yes.
Yeah.
So there is no need for break. I hope that.
No need. We'll continue.
Okay, please, anybody get out of the trainings, come back, because I'm afraid some people they
left.
Let us take it a break. It's better because I'm afraid some people they left.
Whenever you announce
so we
something,
will.
So you announce it. So okay.
Can you just put timer, Mr. Umar, so other can know when we'll start again?
Abdulillah, can you do that, please?
So we're taking a break then?
Yeah, just it's for 10 minutes. Very fast it goes.
Yeah.
Because I'm afraid that people they left already for break.
I see 57 people here, so I don't know if they left or not.
No, they are keeping, on the training course, but they left for a coffee maybe.
Okay. All right. Well, let's wait for 10 minutes then.
Yes, doctor, we can start. Sorry for that.
Okay.
Doctor, we can start.
Yeah.
Yes.
Give me a minute. So, I hope that you can see my presentation.
Yes.
So, can everyone see my my presentation?
Yes, we can see.
Okay, good. All right, so I will continue on then, talking about the second group of items that are to be included in this qualification scheme, reviewers qualification scheme training. So I want to talk about the requirements of 17025, of ISO 17025, with regard to method verification, a little bit of method validation, so make the distinction between verification and validation, and a little bit about ensuring the validity of results as required again by 17025. About this last topic, I will have a lot more to say the second time around. So this is only a preview, let's say, today of what is to come. So what I want to do is I want to look basically at the difference between verification and method validation. I want to present very quickly a verification methodology, and then look into the role of proficiency testing with regard to ensuring the validity of results. And of course, proficiency testing and interlaboratory comparisons, these go together. Okay, so some useful literature I have to mention here, at least to my knowledge, that most of these issues of method verification, of verification and validation of method, really have their origins from necessities that arise in testing, and particularly in analytical laboratory testing. So their validation is a very important topic. On the other hand, for physical metrology and for physical calibration and mechanical method calibration, things are much simpler with regard at least to method validation, because most of the methods that are employed in the calibration lab are based on what are called standard methods, which are given to us through guidelines that are provided by organizations or NMIs. So even though validation is important in the analytical chemistry and biology laboratories, for us it's not that important coming from the physical metrology side. So I will not stress it, as I said, but verification is important, and this is what I will stress today. In addition, so You can find a lot of these terms and methods and discussions on the subject in Eurochem. So Eurochem, for example, deals with all of the details and the requirements with regard to analytical methods and their validation. As far as PTs and ILCs are concerned, and their relationship to accreditation, information can be found on ILAC. There's an ILAC document which provides information on requirements that accreditation bodies should place on their laboratories, on their customers, with regard to participation in PT schemes and in ILCs. With regard to the level and the frequency of participation, the latest and clearest document to my knowledge is a document produced by European Accreditation, which stresses that the new perspective on how to deal with the level and frequency of participation by including elements of risk analysis. So basically, a lot of the responsibility on participation is placed on the laboratory itself. So in the past, there were rules that said that for every discipline, you have to participate so many times within such a time period. The new way of looking at things is to place the responsibility of planning and executing, implementing the plan on the laboratories. And when they plan, the laboratory should take account of the specific issues that are important to them with regard to proving their competence through proficiency testing and ILC participation. So with regard to these two words, verification and validation of methods, ISO 17025 has definitions regarding them. I have to, the word verification is relatively new. It appears for the first time explicitly in this last rendition of 17025. It wasn't present in previous issues of the standard. So it's becoming important, and the distinction between verification and validation is important. So if we look at the definitions, let's see what we can get from them. So as far as verification is concerned, this is defined as the provision of objective evidence that a given item fulfills specified requirements. Okay, so in order to make this a little bit more concrete, instead of the word item, you can place a specific device which is used in order to perform measurements or calibrations. And where it talks about specified requirements, these are the calibration method requirements. So if we do that, let me try to hide this. Then we are talking about, as far as verification is concerned, we are talking about the provision of objective evidence that a deadweight tester fulfills specified calibration method requirements. Okay. On the other hand, when we're talking about validation, we are talking about a verification where the specified requirements are adequate for an intended use. So if we, again, use instead of intended use, for example, calibration of pressure gauges, then we are talking about the verification where calibration method requirements are adequate for the calibration of pressure gauges. So in other words, when we're validating a method, we're ensuring that the requirements of the method are adequate to perform a specific task, a specific measurement task, okay? On the other hand, when we're talking about verification, we're talking about whether a particular method or device or measurement system, when implemented in my specific lab, if that is adequate for the intended use. Okay, so one has to do with the measurement system and its implementation within my specific laboratory, whereas that's verification, whereas validation has to do with whether a particular method is adequate to provide results as intended, fit for purpose. Okay, so it's a fine distinction, but I think that it's there.
So the verification, it should be in my lab?
Yes, so when we're talking about verification, we are talking about obtaining evidence.
Possible to
that,
repeat last part?
I'm sorry?
Can you repeat the last part of your speak?
Yeah, what's the last part though? I can stress again that when we're talking about a verification, a method verification, we're asking whether a measurement system as implemented in my laboratory is adequate to fulfill specified requirements, okay? Whereas when we're talking about a validation, we're asking whether a method that has been developed, okay, is adequate for the intended purpose that it has been developed for. All right. So in calibration, again, I have to stress, at least in physical quantity calibration, then there is there is a limited need of method validation because the methods are pretty much handed to us from organizations or NMIs. Okay. On the other hand, verification is an important aspect, and it's an important requirement, which is explicitly mentioned in the new issue of 17025. So, what does 17025 include as requirements with respect to selection, verification, validation? So, it specifically states that the laboratory shall verify that it can properly perform methods before introducing them by ensuring that it can achieve the required performance. Records should be kept, okay? And in the case that a method is revised, it should be re-verified to ensure that it still continues to provide that the laboratory can actually perform this revised method adequately. Okay, so it's not something which is of a voluntary nature. It's something that has to be done because it's very important to ensure that when someone is implementing a method that is handed down to them by an organization or an NMI, that they can actually implement it within the laboratory. So when we talk about the verification, what are the different aspects to which this can be applied? So in calibration laboratories, we have different equipment, facilities, competencies, and other factors that determine the calibration capabilities. So verification applies to all of these items. So it's required to demonstrate that the laboratory is capable of replicating with an acceptable level of performance a method. So what is acceptable now? That's a question. So it has to be obviously consistent with what the method, the particular method can deliver. So that's what acceptable level in this context means. All methods need verification when they are first introduced in laboratory operations. And it should be noted that a verification does not assess the validity of a method, okay? Because that's part of validation. So we have to clarify in our mind the distinction between these two tasks of verification and validation. On the other hand, the requirements for method validation are much more extensive. There's the laboratory has to validate what are called non-standard methods, methods that are developed by the laboratory, and standard methods that are used outside their intended scope or otherwise modified, and so on and so forth. So validation applies to all situations where non-standard methods or methods used in a non-standard way are involved, okay? When there are changes to methods, the resulting new method has to be validated, and other aspects of the method, such as performance characteristics, have to be relevant to the customer's needs, is what the standard requires, okay? And in all cases, there's a requirement that records are retained. In the case of validations, there's an extensive list of what these records might be within 17025. So the requirements for validation within the standard are much more detailed than for verification. Okay. So why is validation needed? So when a new procedure has been developed by the laboratory, it must be ensured that the method is suitable for the intended use. So again, notice that I'm using the word that the method is suitable, and it can produce the required measurement results. Validation is required to demonstrate that the method is capable of being performed and can meet the required specifications, and that validation is a more demanding process than verification because it's much more involved. The requirements are much more involved than those for verification. So verification is a lighter version of proving that something works as compared to validation. Okay, so as far as method selection is concerned, there are the standard 17025 talks about different types of methods that can be used as found through published information or specified by the manufacturer. So it distinguishes between standard methods and non-standard methods. And what is accepted as a standard method are methods which are published in international, regional, and national standards, published in reputable technical organization documents, published in relevant scientific texts or journals, or as specified by manufacturers of equipment. So the methods obtained through these sources are what are termed standard methods, what are considered standard methods within 17025. And when these methods are applied in a laboratory, in a calibration lab, then they need verification. On the other hand, if a laboratory develops non-standard methods, or if it modifies standard methods, or if standard methods are used outside of their intended scope, then the laboratory needs to validate the method. So there's this existed in the older version of 17025. There's a distinction, sorry, between standard methods and non-standard methods. Fortunately, again, at least within my area of experience and expertise, most of the methods that are used in calibration are standard methods. There are instances, of course, where non-standard methods might show up, and that has to do with basically not the development of new methods by the laboratory, but modification of existing methods, particularly for them to be used outside of their intended scope. Okay, so this could be an issue with calibration labs. So with regard to standard methods, 17025 talks about reputable technical organizations and relevant scientific texts. However, no criteria are given as to what is considered reputable and what are relevant scientific texts, okay? So widely known organizations with long history in publishing calibration methods are accepted and are considered reputable. So OIML, Euromet, DKD, DIN, BSI are organizations which are considered reputable technical organizations. Widely known scientific texts or journals used as reference in a specific field can be accepted, can be an acceptable source of validated methods. So what are such journals? Metrologia, for example, accreditation and quality assurance, measurement, review of measurement instruments, several such journals. However, it doesn't mean that because something is published in a journal, it's also validated. So someone has to check to make sure that such methods are considered to be validated or not. So there's no mention in the standard of a definition of what is considered a standard method or what is not considered a standard method. So it's the responsibility of the lab to actually identify standard and non-standard methods and work accordingly. So what might be some examples of modified standard methods that need validation? So these are just examples that of no particular significance. They're just random examples. So if someone uses DKD as a source, DKD has published several methods for calibration, and one of them is DKD R5-7, which deals with the calibration of climatic chambers. Okay, and within this guideline, a definite number of points of measurement are mentioned. So if the temperature in a climatic chamber is measured at a smaller number of points, then this is considered a modification of the standard method as presented within this guideline. Okay. A use of a different measuring system, which can affect the calibration method, is considered a modification of a standard method and hence needs validation. Or a significant deviation in the uncertainty calculation, that is also considered a modification of a standard method. Okay. So in all of these instances, either a deviation from the procedure, the use of a different measuring system, or the deviation in an uncertainty budget as compared to what is mentioned within a guideline or a standard is considered a modification of a standard method and therefore needs validation. Examples of standard methods that are used outside of their intended scope. So if the method is used to calibrate over an extended measurement range. So if, for example, a particular method mentions that it's applicable to a particular measurement range, but the actual method is used at an extended measurement range, this is considered as a standard method being used outside of its intended scope. In addition, if the method is used to calibrate a different type of equipment, so again, this DKD guideline for the calibration of climatic chambers deals with chambers without air circulation systems of volumes less than 2,000 liters. So, sorry, with circulation, air circulation systems of volumes less than 2,000 liters. So if the method is used to calibrate larger volume climatic chambers without air circulating systems, then this is, again, another example of a standard method being used outside of the intended scope, hence requiring validation. Okay, so you see that validation is required even if a part of a method is used differently. It doesn't mean that, yeah. So the extent of the validation might vary depending on how important this variation is or how extensive this variation is, but that does not change the fact that validation is still required. So what are the steps necessary in order to verify a method? So the purpose, again, of verification is to demonstrate that the laboratory is capable of replicating with an acceptable level of performance a standard method. Okay, so this could be considered an alternative definition of what verification is in this context. Okay, its relationship to verification in legal metrology is very, very distant, by the way. So even though the same word is used, I cannot say that there's a definite relationship between the two circumstances. In general, then, verification involves two basic steps. So method verification. It involves the determination of the requirements of the standard method and implementing them within the laboratory. And the second step is the evaluation of performance characteristics of the method as applied in the laboratory, and confirmation that they are consistent with the method requirements. So I think it's a very rational way of approaching. So you have to identify the requirements of the method, implement them in the laboratory, and then you have to judge whether the implementation is commensurate with what the standard method intended, okay? In order to do that objectively, you need performance characteristics on which to base your judgment of whether the implementation is as intended. So when we say determine the requirements of the standard method, what does that mean? This can be broken up into the different areas which are important when we're performing a calibration. So we want to ensure that the requirements, the identification of requirements have to do with the equipment which is used for the calibration, okay? So we should be using equipment which is equivalent in accuracy and scope as the recommended equipment in the method. It has to do with the environmental conditions in the lab, so the lab should ensure the proper environmental conditions for the performance of the method. With regard to the procedure itself, the procedure should follow precisely the method requirements without deviations or modifications, which would require validation. With regard to controlling of data, data collection, analysis, and calculation should be consistent with the requirements of the method. With regard to uncertainty, the uncertainty model and the estimation should fulfill the method requirements. And with regard to personnel competence, the personnel assigned to perform the method should have the necessary training and experience for the calibration. So all of these are are part of the method requirements that we have to ensure are upheld when the method is implemented within our laboratory. So the second step is to evaluate performance characteristics, which are set so as to so that these method requirements are related to them, and through the use of these performance characteristics, we can determine whether the method requirements are actually upheld or not. So what are some of these performance characteristics which are involved in verification? So identification and control of influencing factors and determination of any residual risks after controlling of the influence factors. The repeatability, if the repeatability and reproducibility of the method are as intended. Measurement trueness and measurement uncertainty, data calculations, and the use of interlaboratory comparisons if appropriate and when available. So all of these are performance characteristics that have to be determined. Well, they have to provide evidence that the implementation of the method within the lab is as intended. There are additional performance characteristics which are more relevant to testing, such as limit of detection or limit of quantification and sensitivity and so on and so forth, which are not really relevant to calibration labs, at least to physical metrology calibration labs. So the basic characteristics which are of relevance are repeatability, reproducibility, influencing factors and residual risks, bias, and uncertainty. So I will not go into the details of redefining what all of these mean. The basic idea is that these are characteristics which can be monitored when performing the verification and can be used so as to conclude whether a method as implemented within the specific lab operates as intended. So I think that we all know what we mean by repeatability, reproducibility, and bias. I will go through them very, very quickly. About uncertainty, we finished talking about that. So this is a generic graph of which shows what is meant by repeatability and what is meant by accuracy, and how accuracy is related to trueness and bias, and how repeatability is related to what is called precision. So I think that all of you are familiar with the differences. We talked about them yesterday also, between accuracy and precision, repeatability and reproducibility, and the term bias, and what the relationship of all of these are with uncertainty. So to make this a little bit clearer, maybe, on this graph, we see on one axis we have the improving of trueness or the decrease of bias in the vertical axis. On the horizontal axis, we have the improvement of precision. So as we move from the origin of this graph to the upper right-hand corner, we have a decrease of uncertainty and an improvement in what is called accuracy. So you can see that by the graph, the bullseye with the dots all bunched up at the center. So upper right-hand corner represents an area where measurements are precise because they are bunched up together, and accurate because they are all near the center. Lower left-hand corner represents a situation where measurements are imprecise and inaccurate. So generally speaking, the uncertainty decreases as I move from the lower left-hand to the upper right-hand corner of this graph. Okay, so the second step is the evaluation of these performance characteristics. The first performance characteristic had to do with ascertaining the residual risks after identifying and accounting for influencing factors on the method as it is being implemented within my laboratory. So what should the lab do in order to exploit this performance characteristic? The lab should identify influencing factors that affect the application of the method and take measures to eliminate or reduce the risks. Okay, so an example would be that a risk is identified in performing a calibration in a laboratory because there are temperature fluctuations which are on the order of plus or minus 2 degrees per hour due to the air conditioning system. So there are several types of measures that someone can take in order to alleviate any influencing factors. and minimize the risks in performing, in obtaining measurements which are not in agreement with what the specific method promises. So one way is to use an insulation enclosure so as to limit the temperature fluctuations. Another way might be, a more expensive way might be to fine-tune the air conditioning system, or even maybe consider upgrading the air conditioning system, the controller actually of the air conditioning system, so as to limit the temperature fluctuations. So the idea is that in order to verify that a method is working in our lab, we have to identify the factors that are influencing during the application of this method, the implementation of this method, and minimize the effect of these influencing factors. With regard to repeatability, the laboratory should evaluate the repeatability of the method as applied in the laboratory, and compare it to what the method actually is designed for. And this is important because, as we saw, repeatability is an important component usually when we're talking about modeling the uncertainty and budgeting the uncertainty. Reproducibility is kind of similar, but the difference between repeatability and reproducibility is the time issue. So when we're talking about repeatability, we're talking about a fairly small time interval in which measurements are performed in order for the repeatability to be determined, whereas reproducibility could be a much larger time interval over which measurements are performed and compared. So the laboratory should also evaluate the reproducibility. It's something that is many times overlooked, but reproducibility is equally important with repeatability, particularly when it comes to ensuring that the results produced by the laboratory are consistent over time. So, well, basically over time. So in order to evaluate the reproducibility of a method as applied in the laboratory can vary the conditions, use different equipment, different operators, and repeat the calibration over a period of time. Okay. With regard to bias, so bias is related to the trueness of a measurement, and they are in fact related in an inverse way. So an increase in trueness means a decrease in measurement bias. So the best way of estimating laboratory bias, or the application, the bias resulting from the application of a particular method in a laboratory, is by participating in some kind of an interlaboratory comparison, so as to be able to determine whether this the magnitude of this bias. Measurement uncertainty. So all of these issues, repeatability, bias, and reproducibility, as well as influencing factors, finally end up in the measurement uncertainty one way or another. So the laboratory must also evaluate the measurement uncertainty and confirm that it fulfills the method requirements. Okay. If there are no such requirements in the method, it should confirm that it fulfills, it's acceptable with respect to the intended calibration measurement capability that the lab wants to validate. Okay. So data calculations are another important aspect of a calibration method. The measurements are one part of the calibration, but the evaluation of these measurements is an often overlooked part of the calibration, but it is of importance in verifying that a method works as intended within our laboratory. So with respect to verifying the method. So the laboratory should ensure that calculations of calibration results and uncertainty are correct. It should be doing this by using test data if they are available, okay, to confirm the calculations. It should do this by using software which is validated, whether this software is used to actually perform calculations, such as spreadsheets, or whether it's software which is used to actually run the system. It should be validated software, either by the manufacturer or provider, which is probably the easiest, or validated by the user, which is could be quite a burden. Okay, and with regard to participation in interlaboratory comparisons, this is another performance characteristic. So how does the laboratory perform the method with respect to evidence from outside of the laboratory? So this is typically done by participation in an ILC. So the overall laboratory performance through an external reference is done this way. And this is another performance characteristic which is used in order to verify the method as being implemented within the lab. So what are some verification responsibilities? Method verification requires higher competence compared to execution of a calibration. So the laboratory should define appropriate competence requirements for persons who perform method verification and authorize them for this. Verification requires resources, so time, competent personnel, allocation of facilities, implementation, the authority to implement changes, possibly the requirement of purchasing of new equipment, etc. And finally, it should be that the verification of a new method should be a planned activity and have the management approval and support. So all of these are requirements with regard to let's say prerequisites with regard to performing verification of a method. Okay, to make the distinction, as far as validation of methods is concerned, the purpose is not to demonstrate that the laboratory is capable of performing a method, but to demonstrate that the method is suitable for the intended use and produces the required measurement results. That suggests that validation is a more complex process as compared to verification, and more specialized competence may be required, and more steps might be involved with additional performance characteristics as compared to method verification. So 17025 says that the validation of a method, of a non-standard method, should be, or of a new or non-standard method, should be as extensive as is necessary to meet the needs of the given application or field of application. So in practice, a newly developed method requires extensive validation to prove its suitability. This is seldomly the case in physical metrology calibration. However, as I mentioned previously, there are situations where deviations from a standard method are possible. So if that's the case, it's required only to prove that the deviation does not affect the method performance. Okay, so someone would perform a limited validation only to the affected part of the method. Okay. In addition, the extent of validation should also be dependent on risk considerations, customer requirements, and intended use of the results, and of costs. So all of these are issues that come into validation because, as explained previously, it's a complex process. So it's probably not worth the cost and the effort to extensively validate something which you only maybe have one customer a year taking advantage of this particular service. Okay, so it's always a balance between cost and effort. So what are the main steps of a method validation? So this could be the description of a method, or is the description of the method, the definition and analysis of the critical points with respect to this particular method, the evaluation of performance characteristics which are related to the critical points. Based on the results of this evaluation of the performance characteristics, a decision on fitness for purpose, and the continuous monitoring of the performance criteria over time. So what are the prerequisites or responsibilities for validation? Method validation, because it's one of the most demanding activities in a laboratory, it requires a high level of competence and experience in the specific technical field. It can only be done by highly qualified personnel who are authorized to perform method validation. Even more than verification, it requires resources in the form of time, of competent personnel, facilities, implementation of changes, and possibility of purchase of new equipment and other things. And of course, just like verification, validation should be a planned activity and have management approval and support. So there are many common aspects to verification and validation, but there are also differences because the intended purpose of each one is different. So this is what you should keep in mind. When verifying a method, your purpose, your goal is different than when validating a method. Okay, so verification of a method means that you want to determine whether its implementation in a particular environment will give results as expected, whereas validation is a process whereby someone decides whether a method is fit for purpose. Obviously, in both situations, you need objective evidence in order to make the decisions, and this is why performance criteria are defined and are used in order to decide with regard to verifying or validating something. So if we were to make, let's say, a one-to-one comparison between the two, so we would say that a verification applies to standard methods, whereas validation applies to non-standard methods. For example, methods developed by the lab, okay? So either developed by the lab, used outside of their scope, okay, or used over an extended range. The verification does not question the validity of the method, okay? Validation, on the other hand, must prove that the method is valid for its intended use. Verification confirms that the lab can perform the calibration, that is, that it uses the right equipment, it implements correctly the calibration steps, it produces consistent results with whatever the method purports. On the other hand, validation is a detailed examination, verification, and documentation of all method parameters using techniques such as reference standards, comparison of results, participation in ILCs, etc. In both cases, records, it's necessary to keep records. Record keeping for validation is much more extensive, okay, than for verification. And in both cases, verification or validation must be done when there is a change implemented within the laboratory method, within the use of the laboratory method. Okay, so this is my brief exposition and of the differences between method validation and method verification. Again, if one thing comes out of this, what I've been talking about is that verification is much more relevant to calibration work. Validation is very, very important in testing, particularly chemical or biological testing. I don't know if you have any questions that might have come up while you were listening to me talk about these things.
Yes, Dr. Chris, please.
Yes?
If I'm going to use an intercomparison ILC for validation purpose, do I have to make the intercomparison with laboratories whose apply standard procedures to validate my non-standard procedures?
I would think that you would want, you would need to, I mean, that could be a way of doing it, but the design of this, the evaluation has to be, you have to be careful in doing that because it's not a simple issue when you're comparing different methods. So I cannot answer, you know, with in one sentence. I mean, it's not that easy. However, if one does this, they should be very, very careful when evaluating the performance comparatively evaluating the performance of the laboratories. Okay, I'm not saying that it cannot be done, but I'm saying that one should be very careful in the evaluation.
Yes, let me ask it in another way. If all the laboratories in the ILC applying a non-standard procedures, and even the results of the ILC were satisfactory, how do we make sure that there is no a method bias or a bias in the whole method? Because we are all applying a non-standard procedure. How do we know that there is no a bias in our non-standard procedure?
Yeah, well, that's what I mean, that it has to be planned and designed very carefully. So I'm not prepared to answer such a specialized, I have to think about it, but it's not, that's what I can say at this point, that is, someone has to be careful. I cannot say something more. There are difficulties and there are peculiarities. So what, for example, chemical laboratories, when they are applying a new method, okay, they do what is called a pilot study, right? So really what we're talking about here is a type of a pilot study in order to determine whether this new method is capable of producing the results that it is intended for. And this is not a simple issue. So you need to have laboratories that know what they're doing. You need to have internally tested the method first. So you have to have robust methods of evaluating the results, and I mean statistically robust methods of evaluating the results. So it's a complex process.
Yes, you're talking if we are going to evaluate the assigned value or the reference value as using robust methods from the results of the participants. And this, even if the laboratories, all the laboratories were competent, how can we evaluate the bias in the method itself if we do not compare with an independent reference value?
Yes, okay. And what's the question?
So in this case, I have to make an ILC with a laboratory who is performing a standard procedure in order to validate my non-standard procedure.
Well, I would think that you would have to perform the method with the standard procedure and the non-standard procedure. Everyone would have to do that and compare the differences.
Yes, that's clear now. Thank you.
But doctor, the question, if we have a standard procedure, why we need non-standard procedures to be validated?
That's, well, I can think of instances where you do need one because, for example, you have a method of determining. So this is very relevant in chemical, in analysis laboratories where, for example, you're using one instrumental method to determine something, but then there's another method which is easier to apply. So you want to test to see if this other method, which is easier to apply, can be used for the same purpose. So again, I'm not a chemist, but I understand that there are standard methods that are used in order to do things in an analytical chemistry laboratory. So for example, in order to determine concentrations, you use, I don't know, I'm just saying now, liquid chromatography in order to do this. But then there might be someone that says, well, I have a spectrophotometer and I will do this using light. Okay? So I want to test to see if this new method that I have, it's capable of producing results which are comparable to what the already existing standard method provides. Okay, so that might be one reason why someone might do it. But this is, it's not something which is very frequent, at least in the setting of calibration labs. There might be some, high-end calibration labs. I'm sorry, can everyone please turn their mics, because I have a noise in my head again. Thank you. So I can imagine that there's a high-end calibration lab which is involved in a very specific type of a measurement that they need to validate in order to prove that it can produce the results that they expect it to do. But you know, on your regular everyday calibration work lab, there's not that many instances where they actually have to validate something. But I can imagine that NASA, for example, their calibration lab are involved in this type of work, or, you know, as I said, some high-end calibration lab. On the other hand, verification is something, again, which is very, very close to routine operation of any calibration lab. Any other question? Okay, if that's the case, I'll move on to the second part of this presentation, which has to do with proficiency testing and interlaboratory comparisons. So I will give you a glance, an overview of what is meant by proficiency testing and the distinction with interlaboratory comparisons, the requirements, and some aspects of how these types of exercises are conducted and the results are evaluated. So, in general, the competence of accredited laboratories is assessed by two complementary techniques: on-site evaluation of the requirements of ISO 17025 and proficiency testing, which involves the determination of laboratory performance by means of interlaboratory comparisons. So this is the first, let's say, not ambiguity, but difficulty here, because in everyday language, we usually use proficiency testing and interlaboratory comparisons in an equivalent way. But when someone looks in detail at what is meant by each one of these two terms, there is a fine distinction between the two. And we will look at them in just a minute. So ISO 17025 has several requirements with regard to ensuring the validity of results. And within these requirements, one of them says that the laboratory shall monitor its performance by comparison with results of other laboratories where available and appropriate. So this where available and appropriate is also important, so keep it in mind. This monitoring shall be planned and reviewed and include, but not limited to, participation in proficiency testing, okay, and participation in interlaboratory comparisons other than proficiency testing. So depending on where someone is coming from, one or the other is more important. And I can tell you right now that for calibration laboratories, what is more important is, well, both. But proficiency in testing, proficiency testing is the activity which is more important. For calibration labs, these kind of blend together. So why would someone want to use ILCs and proficiency testing schemes? Because they are powerful self-help tools which help detect sources of error in measurement results and weaknesses in the methods. They can act as QC measures aimed at process improvement. They provide valuable information concerning the claimed measurement uncertainty. They can point out inadequacies in the internal quality control system of a laboratory. And they many times have an educational component associated with them. So what would ILCs, which are not proficiency testing, be? Because remember, we said we make a distinction between proficiency testing and ILCs. So when we talk about ILCs, what do we mean? We mean that we talk about ILCs when we're talking about the evaluation of the performance characteristics of a method. When we assign values to reference materials and assess their suitability for use in measurement procedures, or when they are used to support statements of equivalence of measurements between national metrology institutes through key comparisons and supplementary comparisons. Okay, what's the common characteristic of all of these activities? The common characteristic is that laboratories that engage in these three types of activities are considered competent laboratories. So their competence is not in question. Whereas when someone is involved in proficiency testing, their competence is judged as satisfactory or not satisfactory through the use of an ILC. So what are the limitation of proficiency testing schemes and ILCs? In general, they're not designed as a diagnostic tool, okay?
Dr. Chris?
Yes.
Can we consider PTs as a tools of method validation? And ILC
Yes.
as well?
Yes, yes. Yeah. So if you remember when I was discussing this with regard to verification and validation of methods, ILCs did show up in proficiency testing schemes. And in fact, they are one of the performance characteristics that should be monitored when verifying or validating a method. So with regard to the limitations, so in general, as I said, they're not designed as diagnostic tool, okay? They cannot be used as a substitute for routine quality control, okay? They're not sufficient means of validating methods or training analysts. Right. So by themselves, they're not sufficient means of validating methods. In conjunction with other performance characteristics, they can be used for that. But it's not a good idea to use them for training analysts because, well, I think it's evident why. They provide an indication only of problems if they are present. and performance of the laboratory is valid only at the time of participation, strictly speaking. So there are limitations, but the advantages are more than the limitations of using them, and that's why they are maybe one of the best tools used in order to um, 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 evaluate the performance of laboratories with respect to the measurements that they perform. So looking at some of the definitions which are taken from the standard, which talks about the requirements for planning and implementing such exercises. When we talk about a proficiency testing, we are talking about an evaluation of participant performance against pre-established criteria by means of interlaboratory comparison. So we are looking at the performance of participants with regard to some criteria. On the other hand, when we're talking about an interlaboratory comparison, we are talking about the organization, performance, and evaluation of measurements or tests on the same or similar items by two or more laboratories in accordance with predetermined conditions. So there's no element of performance evaluation here. A coordinator of a proficiency testing scheme or an interlaboratory comparison is one or more individuals with the responsibility for organizing and managing all of the activities involved in the operation of the scheme. We typically talk about an assigned value when we're discussing about proficiency testing or interlaboratory comparisons, mostly proficiency testing. So what is meant by that? So that's a value which is attributed to the particular property of a proficiency testing item, okay? And it's very important in evaluating the performance of participants in such exercises. An outlier is an observation in a set of data that appears to be inconsistent with the remainder of that set. So these are all important terms. I think the most important and something that is not very well understood by everyone is this distinction between proficiency testing and interlaboratory. I don't know if it's an issue of if there's any real importance in this distinction. At least in my mind, I cannot say that, you know, I place so much importance in the distinction between the two. If someone wanted to make this distinction, then as I said, when we're talking about proficiency testing, we're talking about proving the satisfactory performance of a laboratory, whereas when we're talking about interlaboratory comparison, we're talking about how a laboratory compares with other peer laboratories. Excuse me.
The intra-laboratory, that when we compare what about the intra-laboratory, that when we compare our result with ourselves, with an old like test, or is it okay or no?
It's okay, but it's not an external reference to what your performance is like. So it could be that you have some kind of a systematic error, which in this way goes undetected. So yes, they're good. However, they do not. They're not a substitute for ILCs or proficiency testing. Okay, so as I said, you should have complementary systems of ensuring quality control, and you should have internal quality control measures which are implemented, but you also need external quality control measures to ensure that there's no systematic effects which might go undetected otherwise. Okay, the standard which talks about the requirements for proficiency testing is ISO 17043. Okay, and it specifies the general requirements for the competence of providers of proficiency testing schemes and for the development and operation of proficiency testing schemes. Okay, it's intended for all types of proficiency testing schemes and can be used as a basis for different particular fields of application. It should be noted that proficiency testing is a conformity assessment activity. Okay, so because there's a pass-fail, satisfactory, non-satisfactory decision associated with this. So it's a conformity assessment activity. So PT providers are CABs as per ISO 17011. Okay, there's a whole bunch of requirements within 17043, just like 17025. The requirements are split up into technical requirements and management requirements. The new 17025 is a little bit more elaborate. It talks about, it's a little bit newer. This has been published in 2010, I think, so it's already 12 years old. So 17025 talks about process and resource requirements, but they're pretty much all technical type of requirements. And it talks about structural and management requirements, which are all included here in the management requirements. So what's important about these requirements is that 3 of them cannot be subcontracted. So providers of such services can subcontract many of the components of this service, but the design of the proficiency testing scheme with regard to planning, the data analysis with regard to performance evaluation, and the issuance of the final report cannot be subcontracted outside of the lab. So, outside of the organization who's the provider of this of the proficiency testing scheme.
Doctor, that's really a very important note, because we are seeing, some proficiency test provider that they are, subcontracting even, the whole things, and they are claim that we are PT providers within our area also. So you are highlighting very important things. Something cannot be subcontract.
That's right. That's right. These items cannot, because I mean, this is the final, let's say, a product that is provided to the customer, right?
Yes.
So the responsibility should be with the provider and not with the subcontractors with regard to this final product. Okay, with regard to the selection of appropriate proficiency testing programs, it's the responsibility of the lab, of course, to select, okay, and plan. But accreditation bodies should assist labs in doing this. And in general, it should be noted that accreditation bodies should seek and make available to their cabs information on such exercises. Okay. Providers of such exercises could be organizations which are accredited according to ISO 17043. Information with regard to proficiency testing providers, accredited or not, and such programs can be found on the European Information System on Proficiency Testing Schemes, EPTIS, which is the most well-known, let's say, database for information on this subject. I can show you what EPTIS looks like. So this is the front page. It's maintained by BAM, which is the German Institute for Materials Testing. And you can just click onto the PT scheme database and provide keywords, and it will give you results on recent proficiency testing schemes and intercomparisons which are either running or are available for participation in the near future. Who else can be an acceptable source of such proficiency testing programs? Laboratories which are not accredited, but the accreditation body has qualified competent for the provision of specific proficiency testing. Typically, these are NMIs and calibration and accredited calibration or testing laboratories. In this case, formally, some evidence should be provided of the competence of the provider, and this can be done either through an informal assessment of competence of the provider or through a statement of compliance with 17043 by the proficiency testing provider. So there's no clear requirement as to who can provide these types of schemes, programs, and it's so there are some organizations that are accredited for this according to 17043, but there are also other laboratories that are very competent, and they have a system of in accordance with 17043, even though it might not be accredited. So accreditation bodies in general would accept proficiency testing participation of their cabs in either type of schemes provided by either type of laboratories, either accredited or not accredited, but in compliance with 17043 requirements. Okay, I've compiled the policy for proficiency testing participation of two organizations, accreditation organizations in the Gulf region. So the GCC Accreditation Center. Okay, so with regard to the requirements for CAB participation in proficiency testing laboratory comparisons, for the attainment and maintaining of their accreditation, laboratories and inspection bodies are committed to prove the successful participation in proficiency tests and interlaboratory comparisons as long as they are available and technically and economically adequate. In other words, what this is saying is that it's a requirement. However, it's something that is judged on a case-by-case basis, depending on how realistic it is for someone to participate in it, either because of technical difficulties or because it's not economically, let's say, realistic because of the amount of revenue supported by this particular activity. So in other words, if a particular calibration is only taken advantage of by 1 or 2 labs, then the risk of something being very wrong is small as compared to the situation where 100 or 200 labs are taking advantage of this particular service. So in the former case, participation, if it's not technically feasible, would be on a basis of whether something like this is available. On the latter case, it would be an absolute requirement for someone to find a scheme, such a program, and participate. There are some areas in testing and calibration, it's said by Jack, that suitable PTs do not exist or is not practical. In such cases, Jack and the laboratory discuss and agree on suitable alternative means. Okay. So what are alternative means? Laboratories can participate in any interlaboratory comparisons involving 2 or more laboratories, or can organize them by themselves. The organizer shall have a documented procedure how to carry out the comparison and perform statistical analysis based on 17043, 13528, and the ISO 5725 series. So in other words, if such schemes are not available, then laboratories should organize bilateral, usually multilateral, very seldomly, such exercises, and the organizer shall have a procedure. So there should be a technical protocol which describes how things are going to be done, and there should be a statistical analysis performed in accordance with ISO standard requirements. I should add here, which I didn't see included in the policy, that there should also be means of ensuring the credibility of the comparison when it's organized this way. And that would mean that probably a third party responsible for maintaining the results or attesting somehow that no collusion or any other funny business has occurred between the laboratories who are doing this. Because this is impartiality, confidentiality is a very important issue in this whole process. So Jack requires a successful participation in at least 1 proficiency test for each category where applicable and available, and a 4-year PT participation plan covering all the scope. It also mentions that the extent and the frequency of participation needs to be determined by the CAB, considering external requirements for participation in proficiency tests and associated risks. Okay, so this goes along what I said earlier, that the new perspective on this is that the laboratory is responsible for accounting for and minimizing the risk of participation in proficiency testing programs. So it should plan, and it will be assessed based on this plan, and it should take account of the frequency with which a particular area is included in this plan, based on many reasons. So some of them are listed here: requirements of law, internal measures for quality assurance, the potential risk of false results, the quantity and significance of the performed tests and calibrations, and the qualification of the personnel. AAC is another accreditation body in the region, and they also have a policy with regard to their CABs participating in proficiency testing programs. So all applicants are required to participate, to cover at least one major subdiscipline in each major discipline in the scope of accreditation of the laboratory over the accreditation cycle. So all accredited calibration laboratories shall participate in PT and ILCs for all items on the schedule of accreditation within the accreditation cycle. So this is a little bit more strict because it requires that all rows within the accreditation schedule are associated or are supported by an ILC or a proficiency testing scheme participation. It also mentions that all accredited calibration labs are required to prepare an activity plan. The laboratory may incorporate participation in national, regional, or international organizations. If there are no formal PTs available, again, other interlaboratory activities can be used to meet this requirement, okay, after the approval of AAC. And in order to satisfy the requirement, the report shall be issued by an impartial third party. So in cases where other interlaboratory activities, such as bilateral between accredited or an accredited and non-accredited laboratory, there should be an impartial third party involved who will issue the report. Okay, so what does a typical calibration ILC circulation program look like? So this is a sequential type of, on the left side, a sequential type of circulation scheme. So the reference value is assigned by the coordinating laboratory. So there's a coordinating laboratory which provides the testing item. There's a reference value which is assigned by the coordinating laboratory, and notice the word assigned. So it doesn't mean that they have to determine it themselves, but they can subcontract this to someone else to determine it and then assign it to the test item which is being circulated. This constitutes the reference value, and then the item is moved from one participant to the other in a sequential manner, and the results appear as shown in this graph. It should be that the uncertainty of the reference value is smaller, actually much smaller than any of than the uncertainty made available by any of the participating labs. And that is so that the uncertainty of the reference value doesn't make the interpretation of the lab evaluation difficult. There are other circulation schemes. So there's a star type of a circulation scheme, depending on how quickly someone wants to finish this ILC or what the specifics of the item being circulated are. It might be advantageous to actually use a star type of a circulation scheme. So what's the difference here? The test item is circulated independently between the reference lab and each participant, instead of it going through all of the participants. Or there might be a composite type of a scheme where the test item is circulated to pedals which are attached to the reference lab, and within each pedal there might be several laboratories which actually measure, or several participants which actually perform the measurements and then send the test item back to the reference lab. Then it sends it to another pedal. This pedal returns it, and then finally to the last pedal composed of some laboratories and back. So the type of circulation scheme really depends on the item and the necessities of the particular ILC or proficiency testing. Two aspects that are very, very important with regard to... Hello?
Yes, I have just questions in the previous slide. If one of the participants has an underestimation of his uncertainty, and his uncertainty is less than the uncertainty of the reference laboratory.
Well, okay, but this is a very specific now question, which I mean, yes, it can be done. So it depends on the specifics again. If we are talking about a bilateral type of an exercise, then it's not a good idea to have you know, an uncertainty of the participant which is a lot smaller than that of the reference value. If we have a multilateral type of an exercise, then it has to be examined whether that affects in any way or not. So it depends on the method that is used in order to analyze the results. Typically, when you use averages or least squares in order to analyze results, these are prone to be influenced by either outliers or results with small uncertainties. So someone has to be careful when doing the analysis, okay? I'm not saying that it cannot be done, but again, someone needs to know what they're doing.
Okay, thank you.
Yeah. Okay, with regard to two important issues, with regard to the artifact or transfer standard that is being used in an ILC and or a PT, which are frequently overlooked, and that has to do with the selection and the stability of the artifact. So the artifact, it's very, very important that the artifact is carefully chosen. And it should be carefully chosen because what the purpose of the ILC is to really to validate the uncertainty provided by this by a particular participant. So if the item cannot is not accurate enough to support the claim of the laboratory, then it will not function as intended. So it's very careful to select an artifact that is fit for purpose, okay? And the example that I have here is that it would be inappropriate to send a Bourdon tube pressure gauge of class 0.1, okay, to a lab that wants to validate a CMC of 100 parts per million, okay, because the characteristics of this device would limit the uncertainty of measurement that the laboratory could report to approximately 0.1%. So in essence, they would not be able to validate their claimed uncertainty. So that's one important issue, the choice of the artifact. The second is that the stability is very, very important because, especially if we're talking about a multilateral type of an exercise, because if it's not accounted for properly, then the labs will not be judged. The labs will not be evaluated with respect to the same assigned value. So if the artifact is not stable, then the assigned value will be changing. So if an artifact has exhibited drift, then reference values are usually derived from the mean of the reference laboratory calibrations carried out before and after the measurements made by the participating lab. So it's always a good idea for the reference laboratory to perform measurements, if not in between, at least before and after circulation of the object. When a step change is suspected, the reference values are derived from the most appropriate reference laboratory calibration. So there's an analysis that has to be done here. And this is, again, it depends on the situation. So if everything goes well, then the analysis of the results are fairly routine. But one has to be very careful when not planning, and this happens when the ILC is not planned correctly, because either the artifact is not selected appropriately, or because the artifact is unstable during circulation. So there are two ways of choosing an assigned value, either by using a reference laboratory or through consensus of all of the participants. So what might be the choice of one with respect to the other? Why would someone choose one with respect